Hey guys, so today we're going to be discussing a form of digital to analog conversion. And this form is called Quadrature phase shift keying, so QPSK. So just a brief background, what is digital to analog? Well, digital to analog is the process of manipulating the characteristics of an analog signal in accordance with the provided input digital signal. So there's three different forms or three different types of digital to analog conversion. The first form, amplitude shift keying, manipulates the amplitude of the carrier signal. Frequency shift keying manipulates the frequency of the carrier signal. And phase shift keying manipulates the phase of the carrier signal. And to the right, we see the diagram of each of those three types of digital to analog conversion. Okay. The first diagram clearly shows the carrier signal's amplitude being modified in accordance with the input signal. The second diagram clearly shows the frequency of the carrier signal being manipulated in accordance with the input signal. And lastly, the PSK shows the phase of the carrier signal clearly being manipulated in accordance with the input digital signal. What interest us today is phase shift keying, PSK. So as previously stated, PSK is when we manipulate the phase of a carrier signal in accordance with an input digital signal. Okay. Now, PSK is more commonly utilized than ASK and FSK. Why is that? Well, it's primarily because of the influence of noise. Okay. So noise can affect the amplitude of a signal much easier than it can affect the phase of a signal. Expect the PSK to be less susceptible to noise than the ASK or FSK. So now we're going to take a look at some different types of PSK. Well, Emery PSK is a multi-level digital modulation technique, okay, where there are M different phase angles utilized to represent M symbols. So we'll see exactly what that means in a second. But for now, each symbol is made up of n bits, where m is equal to 2 to the power of n, and we're assuming a uniform spacing of phase values. Now, if we take a look at the diagram to the right, we can clearly see that as we increase the value of m, so the number of different phase angles utilized, our error rate increases. Now, if you want to learn more about why that is, you can take a look at the paper listed below, which goes into details about how increasing the value of m, or the number of different phase angles utilized, has a direct consequence on the error rate. Now, binary PSK, BPSK, is when our m value, so our m, number of utilized angles, phase angles, is equal to 2. Okay. In that case, we will only need 1 bit to represent it. Okay, so either a 0 or a 1. And when we take a look at the diagram to the right, we can see that when we're provided with a digital input signal of 10110, we can accurately manipulate the carrier signal in accordance with that digital signal to provide our respective modulated signal, which clearly has differing phase values. Now, what about increasing the value of m to 4? Well, now we get something called Quadrature PSK. So it's a variant of an Emery PSK, and it allows us to carry twice as much information as BPSK using the same bandwidth. Okay, and we can take a look at the constellations depicted to the right And we can see if we follow the first constellation, we have 0 degrees, 90 degrees, 180 degrees, and 270 degrees, which represent our phases. Okay, or we can follow the constellation to the right of that, which lists our phases at 45, 135, negative 135, and negative 45. Here we can see the QPSK design. And essentially what's happening is that we're taking an input digital signal. In the diagram to the left, we have 0, 0, 1, 0, 0, 1, 1, 1. That input signal is being dichotomized into two different streams. One stream is the even bit stream, and the other one is the odd bit stream. So we have 0, 1, 0, 1, and we also have 0, 0, 1, 1. Now, if you look closely at the QPSK design, you'll notice that there's actually two separate BPSK designs. One in phase and one out of phase due to a 90-degree phase shift. Now, the product of these two BPSKs will be two sine waves, which will be added together, producing our desired QPSK waveform. Now, it's important to note the NRZ encoding prior. And in the next section, we'll be taking a look at how we can implement the QPSK in a Simulink model to achieve the desired results